So, welcome everyone. Welcome to our presentation, So I Became a Node. During this presentation, we are going to talk about vulnerabilities that we describe during an assessment for one of our clients. This vulnerability rely on Azure Kubernetes service, and more specifically on a TLS bootstrap token. So a bit about us. This is Paul Barbé, and
Hello.
And this is Kévin, and I am Kévin Schouteeten. Sorry, we are both pen tester and red teamers at Synactive. Synactive is a French security company. We are 4 departments with pen test, reverse engineering, vulnerability research, development, and response incidents. Here's an overview of what we are talking today. First, I will give you some basic presentation about Kubernetes and give you some definition. Then we will talk about Kubernetes authentication, TLS, and node joining process. Then we will expose how you can exploit this enrollment process in Azure Kubernetes cluster, and why it's not a really good idea to sharing the host network namespace when you create a pod inside the Kubernetes cluster. Then we will proceed with a demo and give you some insight about mitigation. So exploiting TLS bootstrap token, it's not really a new technique. There is a lot of blog posts and documentation on the internet, but especially in Google Kubernetes engine or Elastic Kubernetes service. But when it comes to Azure Kubernetes service, there is nothing. So that's why with Paul, we decide to present this topic here. So what is Kubernetes? Kubernetes is an open source service for automating the deployment, the scaling, and the management of containerized application. So if you look at the screen, this is a basic Kubernetes cluster. At the top, you have the control plane with some component like scheduler, etcd, Kubernetes controller manager, and the API server. All these components are here to handle the overall state of the cluster. And if you look at the bottom, you have nodes. Nodes, it's where your applications are running. Each node run container runtime like Docker, for instance. And node run also pod. Pod is the smallest unit in a Kubernetes environment. And if we look inside the pod there is one or multiple container, and it's inside this container that your application is running. In the node, there is also a component called kubelet. So this component talks with the control plane, and the kubelet receive from the control plane some information, so some specification, and his goal is to apply this specification to the node. Then, if we look at the control plane, I will not describe the scheduler and etcd. However, I will give you some details about the kube controller manager. The kube controller manager runs several controllers, and each controller have a specific goal, like deploy a pod, or generate a new certificate, sign a certificate. As you will see later, certificates are a huge part of authentication and authorization in Kubernetes. And then we'll talk. I will present you the kube API server, which is a really important component in control plane, because this component exposes the Kubernetes API. Now, I will let Paul talk about authentication and authorization in Kubernetes.
Thank you, Kévin. So, before delving into the exploit itself, we will need to understand some mechanisms inside Kubernetes, starting by authentication and authorization. So, authentication and authorization are 2 distinct steps. When you want to perform an action, you will send an HTTP request to the API server, and the caller identity will be extracted thanks to the authentication part inside either HTTP headers or through mutual TLS authentication. This identity will be extracted as a username and a list of groups that will be used by the authorization part to resolve whether or not you can perform the action. So you can implement these two mechanisms in different ways. Regarding authentication, you have mainly three kinds of identities. Sorry. First of all, you will have normal user, your administrator, for example. You will have service accounts and also infrastructure components. For regular users, they are not stored inside the cluster as a resource. You can't list them, you can't create them directly inside the cluster. So all of their identifying information need to be contained inside their credential. And that's why you will find ways like X509 certificates, OpenID Connect with ID token, or an authenticating proxy in front of the API server. So then you will have service accounts that are used inside pods, and for your workload to be able to speak with the API server, they will use JWT mainly. And for infrastructure component, they are mainly treated as a regular user and will be using X509 certificate. For the authorization part, you can use mainly three different methods. There is attribute-based access control, where for each identities you will list all their privileges. Then you have the most used, the Airbag method, where you will group your privileges inside roles that you will be able to bind to your identities. And then in Cloud Provider, you will find a lot of webhook authorization method, where an external API will be called to respond whether or not your identity can perform the action. And then you will also have ad hoc special authorization plugin, like the notarization mod that we'll be speaking in this talk. And we'll also focus on X509 and Airbag. So how do you authenticate with X509 certificate? Firstly, you will have a client certificate that will be signed by a cluster certificate authority, by the cluster certificate authority. And you will present it to the API server. The API server will also have a serving certificate, which is also signed by this certificate authority. And so each end of the communication will verify the other end certificate. As I said earlier, normal users are not stored inside the cluster, so all of their identifying information are in the certificate in this case. And it is as simple as the common name will be used for the username, and the different organization attributes will be used for the group. So in this example, I will be logging as Paul in the group admin and troopers. For infrastructure component, this is almost the same, but you have to respect some condition, and in particular for kubelets, as we will speak about it a bit later. You need to be inside the system cloud nodes group and with a username starting with system colon node colon and the node name, which is really important. So now we know how we can authenticate with a certificate. How can we grant some privileges to our identity using Airbag? So first of all, you will have roles that are typically just a list of rules granting privileges over their own namespace. They lived inside a namespace, a Kubernetes namespace. It is just a way to logically restrict, isolate and group resources together inside a cluster. And you will bind this role to different identities that will, in fact, just grant this privilege to these identities. So service account, external user. You will also have other namespaces, which they are with their own role and role binding. And you will also find cluster role and cluster role binding, which function as their namespace counterparts, but at a cluster level, granting privilege everywhere. So by putting the two mechanisms together, if I log in with my certificate and I want to get pod, so listing the pod, the API server will extract my identity from my certificate and resolve each role that is bound to me to see if I have the needed privileges. In this case, here, this role give all privileges on all resources, so I will be able to perform this action. Okay, so TLS is quite important inside a cluster. Let's have an overlook of all the different communications that are happening and the needed certificates. First of all, you will find the certificate authority that will be used to sign every certificate, almost every certificate inside the cluster. And the API server will have its serving certificate to expose the API. Then, all different elements will has its own client certificate to authenticate to the API server. And also, they will need the certificate authority to be able to verify the serving certificate of the API server. For the etcd database, it is almost the same, but with a different cluster authority, different certificate authority, and the etcd database will have a serving certificate, and the API server will be the client. And it's not all. We'll add some more certificates. So you will have your normal user authenticating with their client certificate, and each kubelet will also expose an API, and so they will need a serving certificate. That will be also signed by the cluster authority, and the API server need a client certificate for these APIs, the kubelet APIs. Moreover, the different kubelets need to have very specific certificate for the node authorization mode to be working. So the purpose of the node authorization mode is to restrict the privileges of the kubelets inside a cluster, because if you have a node which is compromised, the client certificate will also be compromised. And so if you only add RBAC, you will not be able to restrict a kubelet to access information for resources that are deployed elsewhere inside the cluster. So that's a problem. It will lead to lateral movement. And so the role of the node authorization mode is to restrict what a kubelet can do to just access resources that are deployed on the related node. So this is a special authorization mode. It will only work on kubelet identity, so inside the system::nodes group and with the system::node::node name. And it will prevent mostly action regarding secrets, configuration, and volumes. With the diagram, you will have here a node where there is some resources deployed inside the pod, your kubelet with its certificate, and you will find the name of the node inside the certificate. And so if you want to perform an action on a resource, the API server will check whether or not the resource is deployed inside a pod that is also deployed on the node by checking the node name attributes of the pod. If they match, the action will be granted, else it will be rejected. So there is a lot of complexity with all this TLS certificate. You have to provide them on sometimes different servers. You have a lot of them. You have different kind of certificate, client certificate, serving certificate, the certificate authority to provide. You need to have strict condition on your kubelet certificate for the node authorization mode. And what about auto-scaling cluster, where nodes come and go? How do you provide certificate on the fly for them? That's why we have certificate signing request. This is a built-in way to sign certificate inside a cluster. You will send a certificate signing request that can be automatically approved or manually by an administrator. We will see how a little bit later. And it will use special controller, which are called signers. And in our case, we will be interested by the kube API server client kubelet. So how does it work? I want to authenticate to the API server, but I don't have my certificate yet. I will create a private key and a signing request that I will be that I will send to the API server. There, it will be approved by an administrator or automatically if I check some conditions that we'll be speaking a little bit later. It will be signed by a signer, and I will be able to retrieve it and use it to authenticate. But what is missing in this example is that you need some privileges to do that. You need the create, get, list, watch on the certificate signing request object. And for the kubelet certificate, the kubelet client certificate, it's better if they are auto-approved because you want easy deployment process. And so you need a specific permission for that. You need the create permission on this resource that will be only calling not client. So you can grant all of these privileges to anonymous user, but as we will see later, it's bad and it will lead to trivial compromise. So bootstrap tokens were introduced. Bootstrap tokens are credentials that are stored inside the cluster as a secret. They give all the different needed permission for you to be able to create and retrieve your CSR. And they will also give the special permission for node kubelet, for client kubelet certificate. And also, as we'll see, you will be able to verify the certificate authority of the cluster before any further exchange, thanks to this bootstrap token to prevent man-in-the-middle attack. So this is what it looks like. It's the example from the Kubernetes documentation. So it's a secret, so you will find the kind of the secrets. They lived inside the kube system namespace with their name. You will have two different parts, the token ID and the token secret. Both are needed if you want to use it. And only the token secret is secret, as the name implies. And you can also have an expiration date for them, meaning that after this date, it will no longer work. And as we will speak a little bit later, this is not the case in AKS. So what's the overall flow? You want to enroll a new kubelet, so you provide it with the bootstrap token. It will retrieve a publicly available config map containing the cluster authority, and this config map will be signed by the secret part of the bootstrap token. So it will verify the signature, and if it's matched, it will use it for further exchanges. It will create a private key, a CSR, send the CSR to the API server. There, the controller manager will verify that it is a valid kubelet certificate and that you have the special permission for it to be auto-approved. If so, it will approve the CSR. It will be signed by the signer, the Kube API client, the Kube API server client kubelet signer, and the kubelet will be able to retrieve this certificate and use it and start to be working. So now that we know all of these different mechanisms, I will let Kévin present the attack on Azure.
Thank you, Paul. So to perform our proof of concept, we set up a cluster in Azure Kubernetes service. So sorry for the size. I will try to zoom a little. So our cluster run one node pool. In this node pool, there is two nodes. Regarding the version of Kubernetes, we use the version 1.28.5. It's not really the last version of Kubernetes cluster. However, we performed some tests, and the last version of Kubernetes cluster is still vulnerable. Sorry. For the authentication and the authorization, we use Airbag. And for the networking, we are using a Calico network policy. We will see why it's important just after. During this demo, we will often saw the kubectl command line. So kubectl is the official CLI to communicate with the Kubernetes API. This tool allows us to, for instance, list nodes inside our cluster or list pods inside our cluster. And in our lab and in our cluster, there is two nodes, and we will deploy a pod the pod host network in our case. This pod will run on the node on the left. And one important thing, this pod has the host network namespace properties set to true. When you set true to these properties in your pod definition, this means that this pod will share the host network namespace of the host. In other words, the pod and the host will have the same network stack. And you will see later why it's important. In the other side, we will create another pod named pod target. This pod will run in another node, and this pod will have a secret. During our demo, our goals will be to add access to this secret from the other pod. One more important thing, when you deploy an infrastructure in Azure, there is two specific components named wire server and WAA agent. These agents are deployed to share configuration and data when you set up new virtual machine. And one important thing to do to say about the wire server, when you want to access protected settings, you can go to the URL /VM settings, and the wire server will respond with this response. And inside this response, there is a property named protected settings. And inside these protected settings are encrypted with a key that we'll call the wire server key. So if the WA agent wants to access the protected settings, it will have to decrypt these settings. So I will describe how the WA agent will describe the protected settings. Everything starts with the goal state endpoint. So I made a schema. I don't know if everyone saw or if I will zoom a little. Okay. So first, the WA agent will contact the goal state endpoint, as we said just before. The wire server will give to the WA agent the URL for the certificate endpoint. Then the WA agent will generate a self-signed certificate. With this self-signed certificate, he will contact the certificate endpoint and provide its self-signed certificate. Then the wire server will put the wire server key inside an envelope. This envelope is a .p7m file. And after that, the WA agent will decrypt this envelope to retrieve the wire server key. And with this wire server key, the WAA agent can decrypt the protected settings that we saw in the VM settings endpoint. And in our case, why it is important? Because, for instance, if a node cluster wants to join a cluster, as Paul said before, he needs the TLS bootstrap token. And the TLS bootstrap token are in the VM settings, in the protected settings that are encrypted. So if we want to exploit if we want to elevate our privilege from a compromised pod, we'll have to retrieve this TLS bootstrap token. So we have to mimic the comportment of the WA agent to retrieve the bootstrap token. So there is one limitation that we saw during our research. If you try to access the goal state endpoint from a pod that don't share the host network namespace, you will have a timeout error. And our feeling about that with Paul is that Microsoft think it will be a bad thing to allow unprivileged pod to access the wire server sorry. And if we look on the host, there is an IP table rules that drop every packet forward to the wire server. So if a pod wants to talk to the wire server, the packet from the pod will be forward, so the IP table rules will deny the connection. But if a pod shares the host network namespace, in this case, the packets are not forwarded at all, because when you share the host network namespace, you access directly the host interfaces. So these rules don't apply, and you can access the wire server. During this demo, I will describe all steps we will perform during this demo. First, we will leak the TLS bootstrap token from our pod host network, and we will decrypt it. Then we'll use this bootstrap token to create a new pod inside the cluster. Using this certificate, we will be able to list other nodes and other pods. And then we will sign a certificate for nodes where the pod with the secret is deployed. And then we can retrieve the secret inside the pod. So it's time for open our shell. Okay. Okay. So first, we will deploy our lab. So here I just authenticate to the cluster. So as you can see on this cluster, there is two nodes, the nodes 1 and the node 3. Then I will deploy a new pod. This pod is named pod host network, and he shared the host network namespace. So I will create this pod. Then I will create another pod. This pod runs on the node 3, and his name is pod target, and this pod has a secret. Okay. So if we list pod inside our cluster, we see the both pod, host network and target. And we can have more information. The pod host network is running on the node 1, and the pod target is running on the node 3. Then, to simulate the compromission of the first pod, we'll open a shell inside this pod with this command line. Here, normally, when you open a shell inside a pod, the host name of the pod is always the name of the pod. But when you share the host network namespace, the host name of the pod is the host name of the node. So it's a first sign that this pod shares the host network namespace. We can confirm this information by listing all interfaces of the pod. And as you can see here, all interfaces starting with AZV are all bridged to other pods inside the cluster. Other nodes, sorry. So here we will try to contact the goal state endpoint. So this is so we can contact the goal state endpoint. So this is fine. If we try to do the same thing on the other pod that don't share the host network namespace, the command will hang, and we can't access this information. So we return to the first pod, and our goal here is to retrieve the TLS bootstrap token from the protected setting we saw just before. To do that, we will use a certificate that have been shared on the CyberCX blog post. So this script will mimic the will mimic the WAA agent to retrieve the TLS bootstrap token. First, he will generate a self-signing certificate. Then he will retrieve the certificate endpoint from the goal state endpoint. Then he will send his own self-certificate to this endpoint. After that, this endpoint will return an envelope. Then this script will decrypt this envelope. It will unpack the archive inside this envelope. And inside this archive, there is the wire server key. After that, the script will call the VM setting endpoint and decrypt all settings that are encrypted inside the protected settings. So we will run this script. And there it is. We have the TLS bootstrap token, and now we'll use this token to elevate our privileges inside the Kubernetes cluster. Up. Sorry. Up. So first, we'll use this token. We'll create an alias with kubectl using this token. You may notice the server parameters. This parameter is the URL of the API Kubernetes, of the Kubernetes API. If you are completely blind and you just arrive inside the pod, you can find this value inside the environment variable of the pod. So we'll use the new bootstrap token to authenticate to the Kubernetes API. If we list we are part of the group bootstrapper, which is nice. Then if we list our privileges, there is two important things. Paul already described this resource before. The certificate signing request, we can create, get, list, watch, and the create certificate signing request, not client. With a combination with these two resources, we will be able to become every kubelet on the cluster. So it's really nice. So to remember, our goals here is to extract secrets from other pods. To do that, we have to list other pods because we don't have the information. So we will create a new certificate signing request. There is some important things to respect. First, the certificate name. It has to start with the string system column node and then the name. And the group has to be system column nodes. So to generate the certificate, we use a tool named CFSSL. And after execute the tool, we have the CSR file, just here, and the associate private key. Then we will contact the Kubernetes API. We will tell him we want to perform a certificate signing request. We'll give a name to the certificate signing request. We will use the signer kube API server client kubelet, and inside the request, we will provide the CSR file. So here, our certificate signing request is well created. We can list all certificate signing requests inside the cluster. And as you can see, there is our certificate signing request. And more important thing, this certificate signing request is approved and issued. From there, we can print the details of this certificate signing request. And inside this, we have the property certificate, and this property is the sign-in certificate. And we will use this certificate to authenticate as a new node to the API server. So here I save the certificate. You can see the content of the certificate, and I create a new alias, new node. And this time, instead of using the bootstrap token, we use the certificate and the private key. And if we list our new privileges, we are now a node, and we are part of the nodes group, which is really nice. Then I will list the privileges. Ouch. And as you can see here, maybe there is new resource nodes, and we can get, list, and watch, which means we can list other nodes of the cluster. And that's what will we do. So here, if I use my all privileges and I ask to the Kubernetes API, can you give me all the nodes? I have a forbidden error message. But if I use my new privileges, it prints all nodes that are running inside my cluster. We can do exactly the same with pod. So we can list pod host network and pod target. And now we want to extract secrets from pod, but we don't know where are the secrets. So what we can do is print all detail for all pod inside the cluster and grep for the string secret. So here, what we can see, inside the pod target, there is a secret named mySecret, and our goal is to retrieve this secret. So naively, I can try to access the secret directly, but I have a forbidden error message because, as you can see on the error message, there is no relationship between the new node and the mySecret secret. So to extract the secret, we have to become the node that is running the pod that hosts the secret. Here is the pod 3. So I will do the same. I will create a certificate signing request for the pod 3. Then I will send my command to the Kubernetes API. So as you can see here, just here, the certificate signing API is approved and issued. So I can retrieve the certificate and save it. And then I will use my new certificate, my private key, and I ask to the Kubernetes API to give me the content of my secret. And here, everything works. We have the content of the secret. Now I will let Paul lead us to to cluster admin. Sorry.
Hello? Yeah, hello. Do you hear me? Okay. So, yeah, we saw that we can sign a certificate for any kubelet, and so we'll be able to access any secrets or config map used inside any pod inside the cluster. In a real-life scenario, this is often enough because we'll be able to retrieve database credential, server credential, user credential, and yeah, it will be often enough. As we will see, you can also access any service account which are used inside a pod because you will be able to create a new JWT, and in a real cluster, you will find some of them which are quite privileged. So it will be a fine way to escalate to cluster admin. But we are not in a real cluster, and we wanted to find an out-of-the-box privilege escalation. So if I can, yeah. So that's why when we create a cluster, we use the Calico network policies inside the cluster because, as we'll see, it will come with a lot of pre-deployed resources that we will be able to to exploit. So for our privilege escalation, we will be starting by enumerating all the different resources that are present by default in this cluster. And in particular, we will be focusing on the Tigera operator pod and service account. Then we'll be exploiting the previous exploit to retrieve a certificate for the nodes where the Tigera operator pod is running. and we will retrieve a JWT for this service account. We'll see that with that, we'll be able to become cluster admin. Okay, so this is the same cluster, but there is a lot of things that we didn't find earlier because now we are listing the resources inside all the different namespaces. You can find our two pods that we deployed for the first one here in the default namespace. There is a lot of things regarding Calico, which is normal because we are using Calico. A lot of different pods that are here for Azure environment. And you will see here the Tigra operator service account, the pod, the Tigra operator pod. And inside this pod, we can check by getting the details of this pod. There is a service account which is named Tigra operator. Then, by listing the different cluster role binding, we can find that for this Tigra service account, there is a cluster role which is bind to it, which is a Tigra operator cluster role. And if we check all the different permissions for this service account, for this cluster role, this is quite a lot. Yeah, it is a lot of permission. So again, inside a real-life cluster, it will often be enough because, for example, here, if we list just some permission for this, regarding pods, we will be able to create any new pods. So by creating a new privileged pod on every node, we'll be able to escape on every node and compromise any server. But we want to be cluster admin. So we'll check another resources, the cluster role and cluster role bindings, and you can see here that we will be able to create new one and bind cluster role binding. This is a special security feature in Kubernetes. By default, you can't bind roles that are granting more privilege that you already have, to prevent privilege escalation. But if you have the bind permission, you can do what you want. So we will exploit that. We'll reuse our new node certificate that we make earlier. We will check where the Tigra operator pod is running. So here it is on the node number 1. As we will get the pod UID. We'll see why it's relevant later, but we will need that. So we grab it. And so we will create, as before, a certificate for our node number 1. We'll send our certificate signing request and retrieve our certificate. We'll make another new aliases for this node with our certificate that we just signed. And we can ask for a JWT token for any service account that run on this node. So here we want the Tigra operator, and we used the pod name here and the object UID, so the pod UID here. This is for another security mechanism that we didn't speak about. This is to validate the node admission plugin, which will restrict some other thing, and so we need to bound this JWT to a running pod. So we have a JWT, it's fine. We'll put it inside a variable, and we'll be using it to authenticate to the API server. And we can see that, yeah, in fact, we are well authenticated as Tigra operator service account. And we can check also that we have all the privileges that we are expecting, so quite a lot. Yeah, but we're not cluster admin yet, and we want to do that. So we will create a new cluster role binding, just binding the cluster admin cluster role to the Tigra service account. So we just apply this cluster role binding, and here we have all right on every resources. That's what the start mean. We can do anything inside the cluster. And so we are cluster admin. Okay, that's all for our demo. Now let's talk a little bit about what... Oh, yeah. It's better. Let's talk a little bit about what Microsoft has to say about it and what can you do yourself. So this is a quick timeline of our disclosing. We'll just pause it because it's not really important. Microsoft states that, yeah, it is a security boundary bypass, but meh, we will not act immediately on it because it's just at the cluster level. You can't bounce between multiple clusters, so yeah, maybe one day. So they start to work on something after our disclosing, but for the moment we didn't saw anywhere where you can activate it or use it, or so maybe one day. So what can you do yourself to protect the cluster? Not so much. Just don't use pod sharing the host network namespace. There is really few use cases where this is useful, and if you do that, maybe you can do it in a better way. And if you think that you were compromised in the past, bootstrap tokens are a really good way to have persistent inside AKS cluster. As I said, you can have expiration date, but during our test, we didn't find any. So your bootstrap token don't have this in the manifest, and they can be used at least for some weeks during our test. So it can be a good way to come back in a cluster that you compromised. If you try to delete a bootstrap token, it will be ineffective because it will be automatically recreated by a control plane element that we don't see and we don't have any control over. And it seems to be bound to the node pool. So if you want to rotate your bootstrap token, just delete your node pool and recreate a new one. And so to prevent that, maybe monitor your CSR. If you see some strange stuff, some strange certificate or nodes that are signing new certificate, but should maybe not. Yeah, maybe you should look a little bit deeper. So to conclude, AKS is not less secure than other cloud providers. There is some attacks for GCP, AWS, DigitalOcean. Just learn how your cloud provider works so that you will be able to understand the risk and defend yourself. We'll be adding this method to the kubelet mine tool. This is a tool made by Mark Wickeden, which is used to automate all of these node attacks. And if you want to know more, or if our French accent was a little bit too complicated to understand, you can find our blog post describing all of our research. Thank you very much. Thank you to the staff. And yeah, if you have any question.
Yeah, I'm not fully familiar with Kubernetes, but we saw that whenever you are not in the host namespace, there is a firewall rule blocking you from contacting the wire server. Would it be possible as a mitigation to implement a firewall rule directly on the wire server in order to block the request from a node?
The node has to be able to speak with the wire server. So, yeah, no, you can't. No other question? Thank you, everyone.